Where do I want to put arrows on these things? That's right. And what else do you know about these two charges? Anything? I would guess that that looks pretty symmetrical, so I bet the value of those charges in coulombs are probably pretty close to being equal. And what are these lines again?
Electric field.
Yeah, these are electric field lines, okay? So they go from, I'll just say it, I'm not going to write it down, positive to negative. It's the direction a positive test charge would want to go. So you know there's also some non-contact force between positive and a negative magnet, or normally called, we don't call them plus or minus, do we? We call them north and south, poles, if you will. Guess what direction these things go? Kind of the same thing. So the magnetic field lines this time go in the direction a north magnetic particle goes. Okay, that sounds kind of weird. What's probably more helpful is, do they go from north to south or south to north? Obviously they go from north to south, yes. If you got the picture, it's easy. What, are you going to stick that in your noodle? We have these things called compasses, and a little picture of that would be like this. Okay? And I am drawing a pictorial for the solid part is the magnetic part. Now, if I put this in these fields of magnetism, it'll actually look like that. So what is the direction the magnetic part is going? It's heading towards the south. Does that seem weird? Why? So, no. There. That'd be Earth. Ours. We know our compass kind of does that, doesn't it? Yes, it's supposed to be Mars. So that means what? If Earth is a big magnet, and this goes towards what? Yeah, that's where our south magnetic pole is, on the North Pole. Earth upside down at the moment. Have I talked to you about geomagnetic reversal? Every 600 years, this flips. Okay? So previously, this was, the North Pole was the North Magnetic Pole. Right now, it is the South Magnetic Pole. We, as far as I know, we don't know why this happens. But every 600 years, all of a sudden, this happens. It flips. I don't know why. How do we know this? Because we can actually test, like when magma flows through cracks, we can actually test in going back hundreds, thousands of years, because we know the rate of flow that this comes out and hardens and settles at. And we look at the little pieces of iron deposits in there, and they're all pointed this way, and then at some period of time, 600 years later, they're all pointed the opposite way. And then they're all flipped again that way. And so scientists have tried to coincide this with like some mass extinctions and things like that have happened in the past. They say we're about due. Well, it always fluctuates around. It always does move around a bit, right? Because our core is, of course, we believe it to be a liquid. We get magma, so we kind of assume that it is, but nobody's really been there, so we don't know for sure. But it does swirl around and things, right? And it's probably iron because we know it's got some magnetism. So, yeah, kind of weird. But anyway, so our Earth is actually upside down. So, we're doing lots of currents in electricity. What's the relationship between magnetism? Currents can, and if we had more time, we'd be doing this for like several more weeks, right? Currents induce a magnetic field. If there's no magnetic field, we can just put some current through a wire and there will be one. And vice versa. In a magnetic field, we can generate a current. Induce is the word. So when you get, if you take more electricity and things and higher levels, they introduce you to other terms beyond voltage, resistance, and current, like capacitance, inductance, okay, which have their own meanings, but beyond the scope of this course. Okay, and there was a guy, I guess the first guy who kind of played around with this stuff and found this out. And maybe thanks to him, we have these nice inventions called motors, generators, okay? But it's beyond the scope of what we can do. So let's simplify this. For a single wire, use what's conventional current? What do I mean by conventional current? Somebody. Anybody? Yeah, which is opposite to what the actual current does flow, which is the flow of electrons. That's the definition of what electricity is, right? Free electron flow. So the conventional current means goes in the opposite direction. Okay, so we know the big guy we're taking as the positive. So which way does current go, left or right? Yeah, opposite to where these are the electrons, that's the negative side. Electrons go that way. Okay, so this is what we're taking as conventional current. But you guys already know that. Hope so. You're not going to do well on your test tomorrow. Quiz. Okay, so what happens? That's just left or right. What are we going to do if we want current going into my page or out of my page? Because those are also valid directions we're going to use. How about an arrow? If I want my current going right into my page of paper, what we call into the page, That's like the fins on the back of an arrow, right? That's what we do. Because it doesn't just go left and right, it goes up and down. For out of the page then, I'm going to use the point of an arrow. A dot. Or maybe a dot with a circle around it, okay? But if all you see is a dot, that means it's the point of the arrow, means it's coming towards you. So duck. Okay? Make sense? Everyone get it? Yeah? All right? Okay. All right. Okay. What's the relationship between current in a single wire and magnetic field, which we give a symbol to because we don't want to write magnetic field all the time, right? B. B is the magnetic field. It's given by the right-hand rule. So, does everyone have a right hand?
Alicia actually has two left.
Two lefts? Well, I guess you're screwed then. Okay, this should be easy, right? Four fingers, I got it. Why are we drawing that? Because that's your right hand. There'd be on the other side. See? Look, that's what it looks like.
I know. You're talking about the big thing sticking out.
All right, here is a wire. A big thick one. Call it a rod if you want, but it's a wire. If the current goes that way, then you see the direction your fingers are wrapped? That's going to be the direction of the magnetic field around that wire. Okay? Whoop, almost did that backwards. Okay? So, these are all magnetic field lines, okay, around the wire. And there's lots of them, infinitely many, because there's not going to be a spot where it doesn't induce a magnetic field. Here's another picture. If that's it then, and that's the current, which way do I draw my arrows? Do I want the arrow at A, or do I want it at B? Use your right hand. Who likes A?
B.
Who likes B? Three of you? It's B. Put your right hand, your thumb is in the direction of the current. So I'm going to put my thumb like that. Which way do my fingers wrap? Okay, it goes around like that. Okay, this goes underneath, right? That's the right hand rule. Example. Ooh. The B is the magnetic field. Let's just say the magnetic field. Multiple choice. Got 4 answers. A, B, C, or D. What is the direction of the magnetic field at point A? So,
It is the way the current goes.
okay, hang on. Maybe this is a wire.
Oh, I get it. It goes.
And that's the direction of the current.
I get it. It's because you drew that little dot at A.
I don't know if that question makes sense. Yeah, okay. So if X is the current then, let's call the X the current, okay? That's the direction, that's my wire. What's the direction of the magnetic field at A? Well, put your thumb, right hand, not the left one, but you got to do that hand.
Oh, the arrow would join.
Which way do my fingers go? Right at A. Goes to the left.
See, it is funny. Do you even demonstrate this?
That is the normal way.
Pretend it's a rod. Take that.
I'll show you a little something else
You're looking at the
right after this. A solenoid. What is a solenoid? Well, it actually physically is just a wrap of wire. So I'm dotting the back and the front is solid, okay? And this is kind of hard to draw, so I got a little video I'll show you, okay? Because something, I can't say what's the direction of the magnetic field. We need to know where, because it's different at different places when we have a solenoid, a coil of wire. Okay, so B, field, what's going on? Well, we need to know the direction of the current. Which way does current go? That's positive, so that current goes that way. So there's inside the coil, and then there's outside the coil. What is the B field inside? Is it left or right? Put your thumb where the current is and wrap your fingers to where the inside. Here's, like, problem is there's lots of spots to do this, right? Just take it here. Inside, it's going to go left. Okay? So, in here, it goes that way. Okay? But outside, where does it go? These wrap around, right? Okay? So outside, it goes in the opposite direction. We could call that right. So, as promised, yeah, picture's worth 1,000 words, right? Especially one that's animated. The only problem is, I gotta go back. Yeah, well, it's only 8 seconds long. Okay? You see that? See the direction of I. Put your fingers where I is. It doesn't matter where. Put your thumb down here. Inside, it's going left. Put your thumb here. It's still going left. Put your thumb at the top. Inside, it's going left. Just reach the hand. Okay? Inside, we got a magnetic field going left. Guess what happens if we switch the current and go the other way? Then the magnetic field will go the opposite way. Right? Oh, that you mean the arrow? That just means vector. It has direction, right? Yeah. Yeah. Remember, like v, velocity as a vector, we always put the arrow pointing right. Acceleration, I didn't emphasize that in physics, but same thing. Okay, what's this? Is this going to help? 19 minutes? I don't think so. Okay, show you again. That's it. I'm going to stop this and then get a sheet for you. That is just the first right-hand rule, but that's going to be the only one we're going to get. Right?